I'm going to cover a lot of information about solutions in this video. We're going to look at some general information about solutions, how they form. We'll do a little bit of KSP, and then eventually look at different factors that affect solution formation. So again, this is going to be a pretty long video covering a lot of different topics relating to solutions. A little review here first. Remember, a solution is a type of homogeneous mixture. So it's an evenly distributed mixture here in which one substance is dissolved in another. The solute is the substance that is dissolved, and the solvent is the substance doing the dissolving. So if you look at this picture here, you can see the solute is added, and it's pretty much like the solvent is attacking the solute, and it becomes evenly distributed until you get that homogeneous mixture. All right, so the solute is dissolved by the solvent. And just remember a couple terms here. Insoluble is when something does not dissolve, and soluble is when something does dissolve. We did look at different factors that affect the rate of something dissolving. Remember, we're not talking about something does not dissolve. How can we make it dissolve? No, what we're talking about here is if we have something that dissolves, it's soluble. How can we make it dissolve faster? All right, so think about your cup of coffee. If you want your sugar to dissolve faster, well, stir it up. Agitation makes something dissolve faster. Increase the temperature. Hot coffee is going to dissolve sugar much faster than cold coffee would. Also, if you increase the surface area, all right, crush up the sugar and add it to the coffee, it's going to dissolve much faster than if you used sugar cubes. And then obviously use less. All right, so that one's kind of different. If you use less of the solute, it will dissolve much faster. So those are different things that you can kind of look at that would influence the rate of something dissolving. All right, remember, this is a substance that already dissolves. It's just how can you make it dissolve faster? So that was a nice quick review of some of the terms there involved with solutions. There's three different ways to classify solutions. A saturated solution is a solution that has the maximum amount of solute dissolved that it can hold at that temperature. So basically, it can't hold any more. So that's a saturated solution. An unsaturated solution would contain less than the maximum amount of solute that can be dissolved at a particular temperature. So if you had a big cup of coffee and you added a tiny little bit of sugar and dissolved it, obviously that would be an unsaturated solution because it could dissolve a lot more. And then a supersaturated solution is really interesting. Basically, it's kind of like you trick the solution to dissolve more of the solute than it can actually hold. All right. And usually you do this by maybe like warming it up and then more of the solute dissolves and you kind of go past the saturated point. But it's usually very unstable and temporary. Sometimes even the slightest disturbance can cause just a rapid precipitation and a rapid crystallization. All right. So if you had a supersaturated solution, sometimes even a speck of dust hitting that solution can just cause it to rapidly precipitate out. So if you're looking here at the pictures, an unsaturated solution could contain or could keep adding solute. It doesn't have the maximum amount. A saturated solution has the maximum amount of the solute dissolved. So basically, if you started adding more, it would just start piling up on the bottom. And then a supersaturated solution would actually start to form crystals as soon as it's disturbed. So this is a picture here showing a rapid crystallization. You probably had a supersaturated solution that is now rapidly precipitating out. And that's how you make rock candy. Basically, you heat up your sugar water. It dissolves more of the sugar than it can actually hold. And then you have some type of seed, a stick or string. And as it cools, it starts to precipitate out onto the stick or the string. So you definitely need to know these three types of solutions. You need to understand the classification of solutions here on a molecular level for AP. AP asks a lot of questions on a molecular level, and it's something you have to be really good with. If you have an unsaturated solution, remember in an unsaturated solution, you are adding solute and more can continually dissolve because you haven't reached that maximum point yet. So if you look here on a molecular level, the orange substance here is your solute, and then you can see kind of the bluish area would be your solution here. So you can see from an unsaturated solution, if you notice, more of the particles are entering the solution. You can see the arrows are showing that the molecules are leaving the solute and entering into the solution, indicating that they are dissolving. But you still have some that are kind of precipitating out at the same time. If you notice, one of the molecules is leaving the solution and kind of reprecipitating out. It's just that when it's unsaturated, way more are entering the solution than are actually leaving the solution and precipitating out. So it continues to dissolve. When you have a saturated solution, that's when an equilibrium is established. You have the maximum amount of solute dissolved that the solution can hold, and it can't dissolve anymore. So you'd start to see some of the solute start to pile up on the bottom. And if you look closer at this picture, what we mean by equilibrium is that the amount that are entering the solution is equal to the amount of the particles that are actually precipitating back into the solute form. So if you notice here, you have three of the molecules that are kind of entering the solution, but then three of the molecules are precipitating out of the solution and reforming the solute. That's what's happening when a solution is saturated. That's an equilibrium. All right, it's not just, oh, it's saturated and everything stops. No, the amount that's entering the solution is equal to the amount that's leaving the solution. That is a big idea that you really need to understand about a saturated solution, is that it's an equilibrium and still changes are happening. And then in a supersaturated solution, you have tricked more of the solute to dissolve than the solution can actually hold. So you can see here, you have all of the solute dissolved, but then as soon as you get a disturbance, like a little seed crystal, a little speck of dust, a little piece of solid going in there, you have a rapid crystallization and the precipitate forms. Basically, all of the molecules in the solution start to grab onto that and precipitate out of the solution, and you get the solid forming. And you can see that here, all of the arrows are pointing towards the precipitate forming. There's nothing entering the solution phase. It's all coming out of the solution and forming a precipitate. So you need to understand what's happening for an unsaturated solution, a saturated solution with the equilibrium, and then what's going on with a supersaturated solution as well. When you hear the term crystallization, that's just the opposite of solution formation. Instead of solute entering the solution, crystallization is when you have the particles coming out of the solution and precipitating out. Basically, the greater the concentration of your solute particles in the solution, the greater the crystallization that can happen. And that's why when you have a supersaturated solution, that's why you can have a rapid precipitation, a rapid crystallization, because it's kind of oversaturated there. Basically, you just have so many of these solute particles bumping into each other and becoming the solid. So instead of going into the solution, they're leaving the solution and forming the solid, forming the precipitate. An aqueous solution is any solution in which water is the solvent. So that is typically here a lot of solutions. Remember, ionic and polar molecules are going to be dissolved best in water. You can't say like dissolves like anymore. You will have to explain it in terms of the energy associated with the IMFs, which we went through last unit. But we're also going to go through that again in this unit to kind of make sure we really understand why ionic and polar substances dissolve best in water. You can't say like dissolves like anymore. Just two terms in case you see them. Sometimes they might appear on an exam, and if you know what they mean, it just makes the question that much easier. Miscible means something is mixable. So if you have alcohol and water completely mixing, both are polar, so they basically mix, they dissolve. Immiscible is when things don't mix, so like oil and water. All right, so you can see here in the picture, acetone and water completely mixed together, they would be miscible. But then water and methylene, you can actually see that they're immiscible, and you can actually see the layers that are forming. There are two types of aqueous solutions. You have electrolytes and non-electrolytes. Electrolytes are aqueous solutions that form ions. Basically, electrolyte solutions will conduct electric current. You get this when you dissolve ionic substances in water because the ionic substances dissociate. They separate into their ions so the solution can conduct an electric current. So if you put sodium chloride or magnesium chloride in water, that becomes an electrolyte solution because of the dissociation, and it can conduct. A non-electrolyte aqueous solution has a substance that's dissolved in it, but it doesn't form ions, so it doesn't conduct. So you want to think about a lot of like polar substances. If you dissolve sugar in water, it dissolves, it forms a solution, but it's not going to conduct an electric current because sugar is covalent and it doesn't dissociate. All right, so the sugar molecules become surrounded by the water, but it's not going to separate into ions, so it's not going to conduct. So that would be a non-electrolyte, and typically you'd expect this for polar substances that dissolve in water that aren't ionic. I just mentioned dissociation, so we want to make sure that we remember what that is. That's when you have an ionic solid dissolving in water and separating into its plus and minus ions. If you remember, the plus and minus kind of get stabilized by the water molecules. That process is called solvation. All right, it's a process that allows these stabilized ions to stay apart and prevent them from coming back together. All right, so basically the solute becomes hydrated, all right, if the solvent here is water. So if you look at this, sodium, remember, is plus, all right, so when you put sodium chloride in water, it separates into Na plus, Cl minus. So water has regions of charge. It has slightly negative regions, slightly positive regions due to polarity. So in order to stabilize the sodium plus, it turns and points all its negative, slightly negative regions toward the sodium plus, so that stabilizes him and he doesn't want to recombine with the Cl minus. But then since chlorine is minus, water turns and points all its slightly positive regions toward the chlorine to stabilize it, so it doesn't want to come back together with the Na plus. If the water evaporates, the Na plus and the Cl minus will find each other again, and you would reform the salt and you would see it form. All right, so this idea of dissociation where an ionic solid is separating into its parts, into its ions, into its plus and minus. What keeps it apart is this process of solvation. We need to review a little bit more about how a solution actually forms. Remember, there is some IMF stuff to consider here and some energy stuff to consider when a solution is forming. So we know that there's a bunch of interactions you have to consider. You have solute-solute interactions or solute-solute IMFs that have to be considered. You have solvent-solvent interactions. And then when the solute and solvent interact with each other, there's another kind of set of interactions and IMFs there. So we get solutions. Basically, a dissolving takes place when the attractive forces between the solute and the solvent are greater than the attractive forces between the solute itself or the solvent particles itself. All right. Typically, if you have ion dipole IMFs, that's going to be in water polar ionic solutions, and LDFs are going to be more common in nonpolar solute and nonpolar solvents. All right, so we have to make sure we understand why something dissolves in terms of IMFs and energy, and we're going to review that quickly here. So for example here, sodium chloride we know readily dissolves in water since the attractions, the IMFs between the Na plus and Cl minus ions and the water, all right, so that's the solute-solvent attractions, are greater than the attractions that exist between the Na and the Cl itself, which we call solute-solvent, solute-solute attractions, or between the water's hydrogen bonds themselves, which we call solvent-solvent. So basically, the NaCl dissolves because the Na plus and the Cl minus have a greater attraction to the solvent than they do to each other, or than the solvent has for itself. This is an exact repeat from the IMF section, so I'm going to go through this pretty quick. But if you remember, in order to dissolve a substance in a solvent, there's a couple things that happen here. First, you have to overcome the IMFs between the solute particles. So basically, you have to overcome the IMFs in the solute itself. And then you also have to overcome the IMFs between the solvent itself. We call that solvent IMFs. And this takes energy. It takes energy to break these IMFs in the solute and the solvent. All right. But then you have to form new attractions between the separated solute and the separated solvent. When the solute and the solvent interact, you form new attractions, and this is going to release energy. The question here is, though, do you get more energy back when the solute and solvent interact than it took to overcome these original IMFs? If you get more back from the interactions, that's when you'll see a dissolving take place. All right, and we'll review that again really quickly on the next few slides. Remember, you're no longer allowed to say like dissolves like. It's very helpful. You can kind of think about it in your mind. You can say, oh, well, that substance is polar, so it will dissolve in water. That's perfectly fine. But in terms of explaining, you can't say like dissolves like. Again, a very quick review here. Why do polar substances dissolve in polar, or ionic substances dissolve in polar? Basically, there is a large amount of energy required to overcome the IMFs in both the solute and the solvent. All right, it takes a lot of energy to separate those IMFs in each. It's just that when the solute and the solvent interact, all right, and form new attractions, the amount of energy that's released or given back is larger. Okay, so basically, the polar solute can dissolve in the polar solvent because you get more energy back than it took to separate the solute and the solvent. All right, and the same thing would be true for nonpolar interactions. If you have a nonpolar solute dissolving in a nonpolar solvent, all right, takes energy to separate the IMFs in the solute and the solvent. It's just that you get more energy back when the solute and the solvent form new attractions, and that's the key here. You have to have a net gain essentially of energy. All right, energy is given off, all right, in the process here, and it doesn't cost you any energy for the dissolving. And then again, the opposite is true here. If you have a polar solute, it's not going to dissolve in a non-polar solvent, and vice versa, because again, it takes a lot of energy to separate the IMFs in the solute, a lot of energy to separate the IMFs in the solvent, and then when the solute and solvent particles interact here, the attractions are not as great, and you're not going to get as much energy back than it took to separate each of them individually, so it's not going to dissolve here. All right, basically, it's kind of like you spent $5, but you're only getting $2 back, so it's not worth it to do the dissolving here. It takes a lot of energy to separate the solute and the solvent individually, and then when they interact, you don't get as much energy back because they don't have similar IMFs here. All right, so definitely you need to understand why similar substances dissolve and why something like a polar ionic is not going to dissolve in nonpolar here. It's due to IMFs and energy. Cannot say like dissolves like anymore on the AP exam. This slide again just summarizes that information. Basically, if the energy released when the solute and the solvent interact is greater than the energy needed to break the IMFs in each, the substance will dissolve. You basically get more energy back when the solute and the solvent interact, so it dissolves, like sugar dissolving in water readily dissolves. However, if the energy released when the solute and solvent interact is basically lower than the energy needed to break the IMFs in each, then it's not going to dissolve. All right, takes a lot of energy to break the IMFs in the solute and the solvent, and if they interact and you don't get as much energy back, it will not readily dissolve like water and oil. All right, so definitely understand this idea of the solution formation with the IMFs and the energy. We want to look at this solution formation process a little bit more here to make sure we fully understand what's going on with the overall energy change. So there's some steps that take place here in this solvation process. And we've kind of already mentioned this. So when you're trying to form a solution, right, when you're trying to get a solute to dissolve in a solvent, a couple things happen here. First, you have to what we call expand the solute. That's when you break the IMFs in the solute itself. We call that expanding the solute. And we're going to give that a value here. It's a change in energy. We call it delta H1. It takes some kind of energy to do that, right? But then you have to expand the solvent as well. Basically, you have to break the IMFs in the solvent itself, and that also takes a certain amount of energy. So we'll call that delta H2. All right. But then when the solute and the solvent interact with each other, you have new IMFs that are forming. So we'll call that energy change delta H3. All right. So the overall energy change here of the entire solution formation process then would be uh, the delta H1 plus the delta H2 plus the delta H3 here. Essentially, the energy associated with expanding the solute, breaking the IMFs in the solute, plus the energy associated with expanding the solvent, breaking the IMFs in the solvent, plus the energy that is given off here when the solute and the solvent form new IMFs. And that'll give you your overall change in energy for the solution. If you get a positive value for the delta H of solution, this is talking about the overall energy change of the solution, then it's going to be endothermic. A positive delta H means that the solution formation was endothermic and energy is going to enter the system here. So it's going to feel cold. All right. If you get a overall negative delta H of solution, that means energy is exiting. A negative delta H means energy is exiting. So when the solution forms, it would actually feel warm. Typically, most solutions are going to be or have a negative delta H of solution. They're going to feel warm, but you can still get some solutions forming that have a positive delta H of solution. All right, so you got to consider all these parts: the expanding the solute, expanding the solvent, and then the energy change associated with the solute and the solvent interacting. And you add them all up to get the overall energy change of solution. And depending on the sign, that'll tell you whether it's endothermic or exothermic when the solution forms. Let's look at these delta H's a little bit more. So that first delta H1, right, expanding the solute, it's always going to be greater than 0. It's always going to be endothermic, which what that means is every time you break IMFs in the solute, it's going to take energy. And that makes complete sense. If you have to break the IMFs in the solute, it's going to require some energy to be input. All right. It's just that in ionic and polar substances, that's going to take a lot of energy because typically these have stronger IMFs. In a non-polar substance, that value is going to be a little bit lower because non-polar substances typically have weaker IMFs. All right. So then if we look at the delta H2, expanding the solute, or excuse me, expanding the solvent here, you're breaking the IMFs in the solvent itself. Right. This is also always going to be greater than 0. It's always going to be endothermic. Always. It always takes energy to break the IMFs in the solvent itself. All right. And again, it's going to be pretty high here for polar substances because they have stronger IMFs, and it's going to be lower for non-polar substances. All right. And then when you get to your delta H3, when the solute and the solvent now are interacting with each other and forming new IMFs, it's always going to be less than 0 or exothermic. Whenever you have that separated solute particles and the separated solvent particles interacting with each other, energy is always released because of those attractive forces. All right. It's just that how much is released. All right. Polar solute and polar solvent, is going to release a lot of energy. All right. Other substances here, like a non-polar with a polar, it's not going to release as much energy. And that's how you get kind of this difference here in the energy changes. For the separating or expanding the solute, expanding the solvent, always going to take energy. And then when the separated solute and solvent particles interact, energy is always going to be given off. It's just a question of how much energy. All right. So here in this picture, you have your solute and solvent. All right. So if you separate your solvent, that takes a certain amount of energy. Right. If you separate your solute, break the IMFs in the solute, that takes a certain amount of energy. But when these two interact and form the solution, all right, energy is always given off. It's just a question of how much energy is given off. This is just showing you two examples of some solution formations. For example, here a hot pack with magnesium sulfate has a delta H of solution being negative 91.2 kilojoules per mole. And this makes sense. So that means when the magnesium sulfate dissolves in water, energy is given off and it's negative. So you would feel that it gets hot. Ammonium nitrate, though, in a cold pack, when it dissolves in water, the delta H of solution is positive 26.4 kilojoules per mole. That means when the ammonium nitrate dissolves in water, energy is actually entering the system, so it feels cold here. All right. Something to point out, if the delta H of solution is too highly endothermic, so if it's too positive, the solution will not form. Basically, the dissolving will not take place. All right. If you pretty much get a negative delta H of solution, you can pretty much guarantee the solution is going to form. But sometimes if these positive delta H of solutions are too high, you won't actually see the solution forming. We have to understand this exothermic, endothermic solution formation and look at this in kind of these pictures or these graphs here. All right. So if you remember here, anytime you expand the solute or the solvent, that always takes energy. So we see our H or our enthalpy here, our energy on the left side. So if you separate the IMFs in the solute, boom, that takes a certain amount of energy. If you separate the IMFs in the solvent, boom, that takes a certain amount of energy. So this is the amount of energy that you put in already before it even forms a solution. All right, it takes energy. All right, to expand the solute, to expand the solvent, it always requires energy. So now you have these separated solute solvent particles now. They're going to interact and they're going to form new attractions. And you notice energy is given off when that happens. All right. And in this case, probably because, it's a polar solute and a polar solvent, you get much more energy back than you put in. All right. So if you notice here, this is the amount you put in. This is the amount you got back when the solute and the solvent interacted. And the difference here would be your delta H, your negative delta H in this case, because you got more energy given off when they formed the solution. All right. So that's why this one would dissolve and form the solution and energy would be given off. All right. The amount you got out is greater than the amount you put in to separating the solute and the solvent. All right. So you have to be able to look at that and understand this. And then the opposite is true in the picture on the right. So it took energy to separate the IMFs of the solvent. That's the expanding the solvent. And then you had to separate the IMFs in the solute. That's the expanding the solute part. It took this much energy. All right. It always takes energy to do that. And then when our separated solute solvent particles interact and form new attractions, energy is given off. Energy is always given off when the separated solute and solvent particles interact. The question is, though, how much? And in this case, energy was given off, but not enough to offset the amount you put in. Okay, so this would be an endothermic solution if it formed because the amount of energy you put in was not nearly as much, or sorry, was greater than the amount that you got out. Okay, so it took energy to make this actually form the solution. All right, so you need to understand both of these here. All right, so in terms of what's happening with the energy associated, always with, the solute and the solvent always takes energy. When the separated particles interact, energy is always given off or given back. It's just a matter of how much. And we can kind of see the same thing again here from this picture. Here's your solute and your solvent individually. All right, so the first thing we do here is we separate the solute, the expanding the solute part. It takes energy to break the IMFs in the solute. And then we have our solvent. We break the IMFs in the solvent. That's the expanding the solvent part. That takes energy as well. So right now, it took us this much energy just to separate the IMFs in the solute and the solvent. And then when they interact and form attractive forces here for the solution, energy is always given back. All right, so this is how much energy we got back when they interact and form new attractions here. And you can see the amount of energy given back is not equal, okay, to the amount that we put in. All right, so there is going to be a positive delta H of solution here. It basically cost us more energy into separating the solute and the solvent than we got back when they interacted and formed a new solution here. So the question is, how do these solutions actually form when you have this positive delta H? This negative delta H, this lower energy we know from bonding, negative delta H, negative energy is preferred in nature. So how can you actually get substances dissolving even though you have energy needing to be taken in? That would be a positive delta H. All right, so it can happen, but the question is, well, how does that actually happen? Because it's not preferred. Negative delta H is energy exiting the lower energy state is what's actually preferred, but we can still get these solutions forming even though they have a positive delta H. So we want to look at how that can actually happen. We can get spontaneous solutions occurring if there's two things that are met here. So what we mean by spontaneous solutions, that just means no energy is added to dissolve the substance. If you take sugar, put it in water, it just dissolves. You don't need to add any energy to make it happen. It just dissolves. And there's two ways a solution will spontaneously form. First, if you get the energy being lowered, essentially if you get a negative delta H, if it's exothermic, energy is exiting, the lower energy state is preferred, the solution is just going to spontaneously form. You put a solute into the solvent, if the overall energy change is exothermic, it's going to just dissolve on its own. But some of these endothermic solutions still dissolve. All right. Well, it's not going to dissolve because the energy is preferred. We don't want a positive delta H, but there's something else happening here called an increase in entropy. We will talk about this more when we get to thermodynamics, but the basic gist is that when the solute dissolves in the solvent, the disorder or the entropy increases. So that means it will still spontaneously dissolve and form the solution. So the energy is not preferred. We don't get the negative delta H or the exothermic reaction here, the exothermic dissolving, but there's more disorder, and that is preferred. So the solution still dissolves even though it's endothermic. All right. So basically, the idea here is that your solute is very organized. Your solvent, your liquid is pretty organized, but when you dissolve one and the other, you get much more disorder or more entropy, and that's preferred as well. So the solution will still form even though it's not exothermic. So these are the two ways that you can get a solution kind of spontaneously forming. You can see that again in this picture. You have a solid, which would be less disorder. It's pretty organized. Same thing for a liquid. It's pretty organized here, but when one dissolves in the other, you get an increase in entropy or disorder, and that's preferred in nature. Disorder is preferred. And we'll look at this more when we get to thermodynamics. Now we're going to look at this idea of KSP, or the solubility product constant. This is kind of a little bit of information here relating to equilibrium. So we will talk about this more when we get to equilibrium. But basically, KSP is just telling you how soluble a solid is in water. All right, we know that when a solution is saturated, there's this equilibrium established. We saw that on the slide explaining saturated solutions on a molecular level. So basically, you have some solution still in contact with this undissolved solute. So in order to write a KSP expression here, there's some things we need to consider. First, a KSP expression will only look at aqueous species. So you'll never have solids included in a KSP expression. KSP is going to be unitless. Again, it's just telling you how soluble a particular solid is in water. And the coefficients in your balanced equation will become exponents in your KSP expression. So let's just look at a quick example here. When we're talking about KSP, we're talking about a solid. So you pick a particular solid, and basically we're just having that solid dissociate in water, essentially form its ions. But we use an equilibrium symbol here. One arrow going forward and one arrow going back, indicating that the reaction can go forward and reverse. Again, we will talk about equilibrium more when we get there, but I just wanted to give you that basic overview. So you always have the solid substance dissociating into its ions. So BaSO4, the solid, is going to dissociate into Ba2 plus, which is going to be aqueous because it's dissolved in water, and SO4 2 also aqueous because it's dissolved in water. Okay, again, these are the ions, so they have the charges here. If you wanted to write the solubility product constant of this dissolving, all right, you would write KSP equals, remember, you never use solids here in the KSP expression. So the solid's always going to be dissociating into the ions. So you're never going to need to worry about the solid on the left side. You're only going to need to worry about the aqueous solutions here. So this would be KSP equals the concentration of the barium 2 plus times the concentration of the other ion, the SO4 2 minus. Both of these are 1-to-1, so notice there's no exponents with them. All right, we'll look at another dissolving here just so you make sure you understand how the exponents come in here, but that would be a KSP expression for the dissolving of barium sulfate here. It has no units, and you only pay attention to your aqueous species. And you need to understand this idea that the smaller the KSP, the less solid will dissolve. So lower KSP, lower value here, the less that's going to dissolve. That's a big idea that we really need to understand. Lower values, less of the solid is going to dissolve. I just want to make sure you understand here that solubility and KSP are not the same thing. They are totally different. KSP is an equilibrium constant, all right, between the solid and its saturated solution, or the solid and kind of its dissolving ions here. KSP is totally unitless, all right, and as KSP increases, so does the amount of solid that dissolves here. Higher KSP means more solid is going to dissolve. Solubility, on the other hand, is an actual measurement in grams per liters or moles per liter. It's literally measuring the amount that dissolves to form a saturated solution. Okay, so KSP is this equilibrium constant that's unitless, all right, that gives you information about how readily a solid dissolves, but solubility is giving you an actual amount that dissolves. And solubility is affected by other things, including pH, other ions, which we call common ions, and temperature. The good news is here, so they're different. All right, you need to understand that they're different. But if you know the KSP, you can find the solubility of a compound in a problem, and vice versa. If you know the solubility here with a compound, you can actually find the KSP. So I'm going to show you two different examples, but if you can do either of these examples, you can basically see how these questions might be asked for right now in this solutions unit using KSP and solubility. Before we get into the examples, I just want to practice writing another solubility product constant here. So this time, if we have calcium phosphate, which is the solid, and it's going to dissolve and dissociate into its ions, all right? So imagine this is dissociating, it rips apart, it forms three, all right, three Ca2 plus ions, which would be dissolved, aqueous, plus two of the PO4 minus ions, which would also be aqueous. Essentially, the solid is always going to be in equilibrium with its ions. Essentially, it just dissociated. But you have to pay attention to the amounts of each here. And remember, these are ions, they have charges. So if we wanted to write the KSP expression for this dissolving, it would be KSP equals, remember, you don't use the solids. The solids don't participate in your KSP expression, so we ignore the solid completely. It'd be KSP equals the concentration of the Ca2 plus ion to the power of 3, okay? That's what we meant by these coefficients become exponents in your expression, times the concentration of the other ion, the PO4 minus, but it would be raised to the power of 2. All right, so just wanted to give you a little more practice here with writing these KSP expressions. And something else to take note of here, if you're looking at this, notice the 3-to-1 ratio here between the calcium ion itself and the solubility of the calcium phosphate. All right, for every one of the compound, how many Ca2 pluses do you form? 3. So that's a 3-to-1 ratio here. Also, for every one of the compound, you get 2 of the phosphate ion. All right, this is important in problems. Essentially, all right, the concentration of your Ca2 plus, this value here, must be 3 times the solubility of your original compound. So if you know the solubility of the original compound, the solubility or the concentration of your Ca2 plus must be 3 times that value. All right. And again, if you know the concentration or the solubility of your original compound, the concentration of your PO4 minus must be twice that value. And people always get confused by that because they say, oh, well, isn't that taken into account by the 3 and the 2 there in the expression? No, that 3 and that 2 are part of the KSP expression. They have nothing to do with the concentration of the ions. So we have to pay attention to this when we're doing problems, as you'll see here. All right. So whatever this concentration is going to be, it's got to be 3 times the original concentration. And then you'll have to actually cube that in the expression itself. So let's look at some problems with this. All right, so there's only really 2 variations of these problems we need to worry about right now. So let's look at this first one. It says calculate the KSP for Mg3PO42 magnesium phosphate, given that its molar solubility is 3.57 times 10 to the minus 6 molar. All right, so in this version of the problem, we are finding KSP and we're given the solubility of the compound. All right, so this is the first kind of variation of these problems where you're finding KSP given the solubility. The first thing you want to do for these problems is to write out your dissolving equation here. All right, so you take your solid and have it in equilibrium with its ions. So we have our Mg3PO42 magnesium phosphate, that would be our solid, and it's going to dissociate and be in equilibrium with its ions. But it's going to form 3Mg2 plus, all right, aqueous, because remember, it's dissociating, it's dissolving here, plus the other ion is PO4 minus, but there are 2 PO4 minus when this dissociates. And this is dissolved as well. All right, so we wrote our dissolving equation, essentially our solid in equilibrium with the ions. You have to pay attention to the amounts. Now that we have our dissolving equation, let's write our KSP expression. So KSP is going to be equal to here. Remember, you don't worry about the solid at all in the KSP, so you only have to worry about the aqueous ions here. It's going to be the concentration of Mg2 plus cubed, though, because of the 3 Mg2 plus, times the concentration of the PO4 3 minus squared. Okay, so we want to find the KSP. So that means we need to plug in the concentrations here and solve for KSP. So we have KSP equal to, we need the concentration of the Mg2 plus here, right? What they gave us in the problem is the molar solubility of the compound. So they gave us essentially the molar solubility of this. All right, but in order to find the KSP, we need the concentration of each of the ions. But you can figure that out. Based on this dissolving, we know that for every one of the entire compound, there's going to be 3 of the Mg2 plus, and for every one of the entire compound, there's going to be 2 of the PO4 3 minus here. All right, so that's going to play a role here because we know the concentration of the original compound. So we know the concentration of this, and then we can figure out this then. The Mg2 plus has got to be 3 times that amount. And since we know the concentration of the original compound, the concentration of the PO4 3 minus has to be 2 times that value. So we can plug this in to our KSP expression. So our concentration of Mg2 plus is going to be 3 times the solubility here of the entire compound. All right, but it still has to be cubed. All right, just because you're timesing the solubility by 3, you still have to cube it because that's part of your KSP expression. All right, times the concentration here of your PO4 3 minus, which we said is got to be 2 times the concentration of your original compound. And again, that's got to be squared because in the KSP expression, whatever the concentration of the PO4 3 minus is, it has to be squared according to that expression. All right, so now you're ready to just plug in and solve here for KSP. Be very careful with your parentheses, be very careful with your math, but if you plug and chug this correctly here, I strongly urge you to make sure you can put this in your calculator and get this value. We're going to base it off of the sig figs of our molar solubility, so we'll have 3. It's going to be 6.26 times 10 to the minus 26. All right, that's the value you should get here for the KSP. And if we look at this, remember what KSP tells us. Solubility is telling us the amount that's dissolving, but KSP is telling us how soluble the solid is. So we said the lower the KSP, the less soluble a substance is. So if you look, it's to the negative 26 here. That's telling you that magnesium phosphate is not very soluble. And if you look at your solubility rules here, we said that phosphates are typically insoluble except for the alkali metal or ammonium phosphate. So it makes sense that this value is very, very low because according to solubility rules, it's not going to be that soluble. So the KSP here tells us how soluble a solid will be. All right, so this is the first variation of one of these problems where you would be given the molar solubility of the compound and asked to find the KSP. Now let's look at the other version of this problem. So in this problem, we want to find the solubility of CaF2 and the concentration of each ion given the KSP. So it's kind of reversed. This time we're given the KSP and they want us to find the solubility. That's the other variation of the problem that we need to worry about here. All right, but just like the previous example, the first thing you want to do is write your equation for the dissolving. All right, the calcium fluoride here is going to be your solid, CaF2, and it's going to be in equilibrium with its ions. It's essentially going to dissociate here. It's going to form Ca2 plus, which would be aqueous, plus 2F minus. Be careful of that. And this is also going to be aqueous here. All right, so you always, no matter which version of the problem, write your dissolving equation here first, write the dissociation of the solid into its ions. Just remember it's in equilibrium. And then, just like before, you're going to write your KSP expression. So KSP here is going to be equal, all right, we don't pay attention to solids, so it's just going to be equal to the concentration of Ca2 plus, there's no coefficient with that, so it's just to the power of 1 essentially, times the concentration of F minus squared though because of the 2 in front of it. So now we have our KSP expression, all right? And this time we know the value of the KSP here, all right? So when we start plugging in, we're going to know this value because they gave it to us in the problem. But we're trying to find the solubility of the compound and the concentration of each ion. So when I go to plug this in, I don't know the concentration of this ion or the concentration of this ion, but I know a little bit of information here, okay? So you got to kind of think about this logically. Whatever the concentration of your CaF2 is, let's just say that's X, right? I don't know what that concentration is. But what I do know here by looking at this dissolving equation is that whenever CaF2 dissolves, there is a 1-to-1 ratio between the CaF2 and the Ca2 plus. So if you know this concentration is X, well, then the concentration of your Ca2 plus would also be X, all right? But then when you're looking at the concentration of your CaF2, whatever that value is, you need to realize here that the concentration of the F minus is going to be twice that value, all right? Because it's a 1-to-2 ratio. Okay, so we would assume the concentration of F minus would be 2X. So now you have kind of something to work with here when you're plugging in. So let's plug in here. We know the KSP is 4.9 times 10 to the minus 11th. And this is going to be equal to the concentration of Ca2 plus. Well, according to what I just set up, the concentration of Ca2 plus is going to be X here, times the concentration of F minus. Well, we said the concentration of F minus would be twice that value because of the 2 in front of it. But according to the KSP expression, it still has to be squared. Just because you're multiplying the concentration by 2, you still have to square it according to the KSP expression. So now you're just going to solve for X here. X essentially is the molar solubility of the compound. X would also be the concentration of your first ion, your Ca2 plus, and then you just have to multiply that by 2 to get the concentration of the F minus here, or your other ion. So just be careful with the math here. Essentially, when you do this, you're going to have your 4.9 times 10 to the minus 11th equal to 4x cubed. Be careful there with the math. You would divide both sides by 4, all right? And then you would get here x cubed equal to 1.225 times 10 to the minus 11th. Take the cube root, all right, of both sides. And when you do that, x should come out to be, with correct sig figs here, according to the KSP, 2.3 times 10 to the minus 4th. And because you are finding a solubility or a concentration, this has units of molar. All right, so be careful with that. KSP is unitless, but solubility and concentration has a unit of molarity. All right, so this is essentially the solubility of the CaF2. X is the solubility here of the CaF2. So the concentration of the CaF2 is equal to this 2.3 times 10 to the minus 4th molar, because it's a concentration. And then because of the 1-to-1 ratio between the compound and the Ca2 plus, the concentration of the Ca2 plus is also equal to 2.3 times 10 to the minus fourth molar. But then the concentration of the F minus has to be 2 times that value. So it's going to be 4.6 times 10 to the minus fourth molar. All right. So these would be the concentration of the ions and the solubility of the compound itself. All right, remember, these have units of molar here. KSP has no unit. So now you've seen both variations of these problems. If you just focus on each of them, you pretty much should be able to do any problem I can throw at you for solutions and KSP for right now. For the last part of this video, I'm going to go through the different things that can affect solubility, so affect dissolving here. The first thing is we have to consider structural effects. So we know that polar substances are going to dissolve in polar. Essentially, if you have more sites of hydrogen bonding, a substance would be more soluble. So if you're comparing substances and you see that a particular substance has more sites of hydrogen bonding than another substance, the substance with more sites of hydrogen bonding is probably going to dissolve. There are some vitamins that are water soluble because they have a lot of sites of hydrogen bonding. And then we know that non-polar substances are going to dissolve in non-polar substances. We've already seen that, talked about it with the IMFs and the energy. And another thing to consider here about structural effects, as a chain of hydrocarbons becomes longer, the molecules become less soluble in water and then more soluble essentially in non-polar. And basically, the way you want to think about it is just because as these chains of carbons get longer and longer, they're just going to become too big essentially to dissolve in water. So if you look at something like methanol, all right, methanol has hydrogen bonding here. It's very soluble in water. But then as you add carbons here to get to butanol with 4 carbons now, it has hydrogen bonding as well, but it's only slightly soluble in water. And then by the time you get up to a chain of 8 carbons for octanol, it's not very soluble at all, even though it has hydrogen bonding. All right. So these are just some structural effects to watch out for and how they might affect solubility. So again, just to reiterate, if you have more sites of hydrogen bonding, you can expect molecules to be more soluble in water. So here's vitamin A at the top, has 1 area of hydrogen bonding. It's not going to be very soluble versus vitamin C, which you can see has a bunch of areas, 4 different areas where hydrogen bonding can occur. So it's going to be much more soluble in water. All right, same thing over here on the left. Cyclohexane, which has no sites of hydrogen bonding, is going to be insoluble in water versus glucose, which again has multiple sites of hydrogen bonding. It's going to be much more soluble in water. Pressure also affects solubility here. Important to remember that pressure will basically have no effect on liquids or solids dissolving. All right, if you increase the pressure on a solid, it's not going to dissolve any more or less. All right, same thing for liquids. If you're trying to get a liquid to dissolve, increasing the pressure really doesn't do anything. Don't fall for any tricks. That's very important to remember here. However, a gas will increase in solubility as you increase the pressure. So if you increase the pressure on a gas, more of it will dissolve. And this is why sodas are bottled under high pressure, all right? Because of the high pressure, more of the CO2 will dissolve in the soda. And then notice, as soon as you open the top of the soda, you hear the psh, that's the CO2 coming out because you now have essentially dropped the pressure, so less of it's going to dissolve, and you can immediately hear it coming out. All right, so pressure has no effects on solids or liquids dissolving, but greater pressure will make a gas solubility increase. That brings us to Henry's law. Basically, Henry's law says the amount of gas dissolved is directly proportional here to the pressure of the gas above the solution. So greater pressure, greater the solubility here of a particular gas. All right, it's a proportional relationship. The equation we're going to use for this is S equals Kp. This equation is not given on your equation sheet. So if you need it on a quiz, exam, I will give this to you. I just don't tell you what the letters mean. You have to kind of know how to use it. But basically here, S is the concentration. Usually it's in molarity of a dissolved gas. So essentially this is the concentration of a gas that is dissolved. K is a constant here for the particular solution you are looking at. And then P would be the partial pressure here above the solution. Okay, so typically here this works best for dilute solutions of gases, but we're just going to do a quick problem with this so you can see kind of how to plug in and use this equation to figure out the concentration of a dissolved gas at a certain pressure here. This problem says we have a soft drink is bottled so that a bottle at 25 degrees Celsius contains CO2 gas at a pressure of 5 atms over the liquid. Assuming that the partial pressure of CO2 in the atmosphere is 4.0 times 10 to the minus fourth atms, we want to calculate the equilibrium concentrations of CO2 in the soda both before and after the bottle is open. So essentially here, we're doing two problems. We're doing a before and an after. And they're giving us the Henry's law constant for CO2 as being 0.031 moles per liter times ATM at this temperature. All right. So again, it's going to be two problems here. So we're going to do a before and an after. So let's start with the before. Remember, the equation we're going to use here is S equals Kp. All right, S is the concentration. I am trying to find the concentration of CO2 both before and after you open the soda. So we're solving for S here. So before, S is going to be equal to K, which is the Henry's law constant. It's going to be 0.031 moles per liter times ATM times the pressure. Well, before you open the soda, right, the soda is bottled under a pressure of 5 atms. So that's the pressure here before you even open the soda. So when you solve for the concentration here, that's what S is, you get 0.16 molar. So before you open the soda, the CO2 is dissolved in the soda to a concentration of 0.16 molar. But then after now you open that, all right, we change the pressure. We're opening the can and we are essentially lessening the pressure. So we want to see what happens to the concentration. Again, we're going to be using S equals Kp. We're solving for the concentration, or S here. K is going to be the same constant again. So it's going to be 0.031 moles per liter times ATM. And we're going to times this by the pressure here. And essentially, this is telling us that when we open the can, the atmospheric pressure here, partial pressure of CO2, is going to be 4.0 times 10 to the minus fourth ATM. All right, notice here your ATMs cancel, and that's why you get moles per liter or molarity. So when we solve for S now, all right, we plug in chug, we get 1.2 times 10 to the minus fifth molar. So this makes complete sense why you hear the CO2 coming out, because before you open the can, it's dissolved to a point of a concentration of 0.16 molar. But after, at the concentration here, the partial pressure in the atmosphere, the concentration is going to be way less. So that CO2 has to come out of the solution, and only a little bit of it will be dissolved. So that's an example of a Henry's law problem here using S equals Kp. This is just showing you Henry's law here kind of in picture form on a molecular level. Remember, understanding things from a molecular level is very important for AP. So if you have a particular gas here, a dissolved gas, basically, eventually it would reach equilibrium here in a sealed container. The amount of gas kind of leaving the solution would be equal to the amount of gas that is entering or dissolving into the solution. As you push the piston down and increase the pressure, notice what happens here. You still have some of that gas leaving the solution. It's just that now more of the gas, you can see the black arrows going down, more of the gas is entering the solution and being dissolved. Okay, so that's very important. So when you get to this, eventually a new equilibrium, once you kind of hold the pressure steady, again, you will reach equilibrium where the amount of gas leaving the solution will be equal to the amount of gas entering the solution. But if you compare here with more pressure, you can look here on the right, there's definitely more of the gas dissolved compared to the picture on the left. All right, so a new equilibrium will be established, but when you increase that pressure, you got more of the gas to dissolve here. And that's what you would expect. As you increase the pressure on a gas, more of the gas will dissolve. Temperature also affects solubility. So first we're going to look at solids. If you increase the temperature here, it will cause solids to increase their solubility. So if you increase the temperature of a solution, more of the solid will dissolve. Gases are reversed here. All right. If you increase the temperature of a solution, less of the gas dissolves. All right. This is why global warming and thermal pollution is bad, because if you raise the temperature of the water, there's going to be less oxygen dissolved here for the organisms living in it. All right. So solids is proportional. If you increase the temperature, you increase the solubility of the solid. Gases are inverse. If you increase the temperature, less of the gas will dissolve. So in this picture here, you can see a bunch of different gases. Temperature here on the x-axis, solubility on the y. As you increase the temperature, you can see the solubility pretty much of all the gases here goes down. You see a lowering here of the solubility of gases with increasing temperature. Just want to make sure we can look at these graphs and get information here about solubility. So over on the left, this is showing you solubility of different solids with temperature. So as you increase the temperature, what happens to the solubility of these solids? Typically here, as you increase the temperature, you expect the solids to increase in solubility. And for the most part, that's what you see. You see a general increase here for most of them. You might have one being an exception, but for the most part, they're all going to increase their solubility. What's really neat about this graph is that you can actually see how much of a solid would be dissolved at a particular temperature. So for example, if you were looking at KNO3 here, and you wanted to know how much of that solid could be dissolved, say at 30 degrees Celsius. So at 30 degrees Celsius, you can see here for KNO3, you're going to have a little over 40 grams of it that would dissolve for every 100 grams of water. Okay, so even if we said at 30 degrees Celsius, it's 45 grams. All right, so what that means is if you had a temperature of 30 degrees Celsius here, for your KNO3, you could put 45 grams of it in 100 grams of water and it would totally dissolve. All right. But if you were at 30 degrees Celsius and you tried to add, say, 60 grams of the KNO3, it wouldn't dissolve because at 30 degrees Celsius, it can only hold about 45 grams. All right. And the other graph over here is again showing this with gases. As you increase the temperature, the solubility of these gases is going to decrease. So it's kind of opposite here of the solids. Definitely understand all these factors that can influence the solubility here of different substances.